Hello everyone, so this is just a recording of today's lesson. The goal today is to be able to decide if relation is a function that is in various forms. So let's just start with a little bit of review of what is a relation. What does that have to do with the domain, range, and a function? Or how do those definitions work with each other? So let's start with the beginning. A relation is literally just a set of ordered pairs. Now, specifically what an ordered pair is just a fancy way of writing a relationship between two different numbers. Now, if you remember, we always list our x first, followed by a y, then we put parentheses around that specific relationship. So when you have a relation, it's the set of all ordered pairs for a specific situation that you are talking about. Your x is always going to be in relationship with the y, and so forth and so forth. Now, a domain is just a very specific part of a relation. When we're talking about domains, we're talking about the set of x values of all the ordered pairs that I give you for that specific relation. So let's write that down. Now, if you remember, x values are pretty much the same thing as inputs. Depending on what we are doing, you probably want to focus on x values and inputs given the situation. But for now, just keep in mind that domain are just x values of a specific relation. So it's all the values that are listed first. Now, if domain are the x values slash inputs, the range is the set of y values. And remember that y values are the same thing as outputs as well. So when you think of inputs and outputs, it's more when you're talking about specific functions and equations. But since we're just kind of thinking of basics here, x values and y values for each of those vocabs are going to be just fine. So again, relation, a set of ordered pairs. Ordered pairs are just a relation between two numbers. X is listed first, followed by your y. The domain are those specific x values of all those ordered pairs, and the range are the y values. Now, a function is just a very specific relation. A specific relation in which every x value has exactly one y value. So this function might seem very, very straightforward, but you notice it could get really tricky. That always happens when you deal with something that seems so simple that at times little things get overlooked. But again, we'll work on these a little bit more. We're going to work on all these actually, just to ensure that you understand what does it mean to have a relation, a domain, and range, and how to know if a specific relation is a function. But make sure you write these down in order to reference them later, especially the sense, because it's going to come up a lot later, and you need to make sure that you're training your mind correctly to understand what a function is. All right, so let's go ahead and test our understanding of those first three. So you'll notice here that I gave you a table with a certain amount of information. Now, the information is telling us the average and maximum lifetime for some animals. So you'll notice that if we have a cat here, the average life is 12. The max that one's ever lived is 28. If we have a cow here, they live about an average of 15, and of course the max is 30. Now, I'm not sure if this is actually true. I just pulled this information from a book, but the moral of the story is, you'll notice that we have two sets of numbers that are related to each other. Now, the bottom directions are asking us to represent the following average and maximum lifetimes as ordered pairs. So, just as I explained above, whenever you have an ordered pair, you have an x written first, followed by the y. Now, if I look at all these tables, I can see that I have a 12 followed by a 28. So I'm going to write that as an ordered pair. Don't forget to put your parentheses. Don't forget to to list your x first. Now, notice that this is the first ordered pair. I'm going to go ahead and write all the ordered pairs with the numbers that are in relationship with the numbers across from it. So here's 15 and 30. Next one is 8 and 20. 12 and 20. And finally, 20 and 50. Now keep in mind what I did there is pretty much take the background information. This is what a lot of math people do. Notice that when we started off, we had a table with all these animals, average lifetime, max lifetime. What we're doing is we're pulling out the numbers. We're pulling out the relationships between the numbers, and we're going to concentrate on the actual math in order to pull patterns from there to help us pretty much figure out things from that information. Now, before I go, notice that I just listed every x and y every ordered pair. In order to tell the reader that I am done listing, I'm going to put these fancy math brackets to tell the reader, hey, I've listed everything that has to be listed. Now let's go ahead and locate the domains of all my ordered pairs. Now you'll notice that it's pretty easy to find the X values within a table, but you also need to know how to do it as an ordered pair. Now remember that your X values are always the numbers that get listed first. So notice I underlined all my X values. All I have to do is list them. Now notice that 12 is my first one, 15, 8. Now I see that I also have another 12, but I've already listed it. So make sure that you don't list values more than once. Unfortunately, if you do, you'll be marked down because you are wasting the reader's time. So notice I've listed all my values I am listing, so I'm going to make sure to put my fancy math brackets. So what did I do there? I had a set of ordered pairs in this first problem, aka a relationship between all the numbers and some other set of other numbers. First thing I did here was locate all the X values, the inputs of each and every single ordered pair. Now I'm going to do that for the range. Now again, my range are my Y values, which is all the second numbers that are listed, which start with 28, 30, 20. Now there's that 20 again, but I'm not going to write it down because no need to. I've already listed it. And my fancy math brackets tell my reader I am done listing. Now keep in mind that order doesn't matter. You're just listing items. So once you've listed every single item, you're good to go. Don't forget those fancy math brackets. Now, okay, so I have a set of ordered pairs. I know how to pull the domain from each of those ordered pairs. I know how to find the range of each of ordered pairs. Now, it's your job to analyze each of those pairs and tell me whether it is a function, aka does every single one of these X values have exactly one Y value. Now, let's go ahead and think about this. This 12 is an X value. It has a Y value of 28. Is there any other 12 that has another Y value? And the answer is yes, because if you notice here, these two X values are the same. They have two different Y values. So this is not a function, because the X value 12 has two Y values, and those Y values are 28 and 20. So as you can see here, when you're looking at a bunch of ordered pairs, it's pretty hard to decide whether something is a function or not, because it's hard to visually see. There's a bunch of numbers scattered everywhere. So the next thing we're going to cover here is how to do mapping diagrams, because mapping diagrams are literally just visuals to help us figure out if a relation is a function, aka if every single X value has exactly one Y value or output. So let's go ahead and do that. So like you see here that I have a set of ordered pairs. Now they listed everything here. I have 3 ordered pairs. On mapping diagrams, you always want to start out with a big oval. That is where we're going to list each one of our domain values. I see here that my X values are -3, 0, and 2, so let's go ahead and write those there. Then I'm going to go ahead and write my ranges in an oval to the right. And let's go ahead and figure out what those Y values are. It's just a 1, 2, and a 4. Now keep in mind, just like before, when I was listing my domain and range values, if something repeats, I'm not going to write it down more than once. Now, just as this problem suggests, it's mapping certain values. You're mapping the relationship between these domain values and the range. -3 is in relationship with 1, and arrow is going to show me visually that it is in a relationship. 0 is in relationship with 2, so there's that. And then 2 is in relationship with 4, so I can see here that I have an arrow pointing from every domain value to each one of my Y values, which is my range. Now, is every X in a relationship with one Y? Is this X going in one direction? Yes. How about this X? Yes. This X? Yes. So is this a function? Yes. Let's go ahead and do the same thing for the second one. Here are my domain values. Here are my range values. I can see that my domain values is just an 8. I'm not going to repeat because, again, you'll get marked down because you need to know your maps. 1, 2, and 4 are my range. Let's go ahead and do some maps. I can see that 8's in relationship with 1, 8's in relationship with 2, and 8's in relationship with 4. So does every X value have one Y value? The answer is no. This specific X value has 3 ways to go to 3 different Y values. So no, this is not a function, because the X value of 8 has three y values. Now keep in mind that if you have a function, all you have to do is tell me yes. If it's not, I want you to tell me the specific value that makes it true, aka which x value has more than one y value. Let's go ahead and find the other one. Last but not least here, domain range. Notice that my domain here is a -3, 0, and 2. Notice that my ranges are 1, so luckily for me there's not too much to do. -3 is in relationship with 1, 0 is in relationship with 1, 2 is in relationship with 1. I just saw those relations from the ordered pairs. Now, does every x value have one y? Now, this is where it gets tricky. Does this x value have one direction? Yes. Does this x value? Yes. Does this x value? Yes. So yes, this is a function. Keep in mind that we don't care how many x's y's have. We only care about how many y's x's have. So make sure that you are double checking and you understand what makes something a function, especially with these mapping diagrams here. All right, so there are two kinds of graphs that I want you guys to be able to work with and also categorize. Now, one of them is what is called a discrete graph. A discrete graph usually consists of a lot of little ordered pairs, random dots that are not connected, just like I've shown above. Now, these dots could be really anywhere, these coordinate points, but the main point here is that there is some type of disconnection going on. That is what a discrete graph. A continuous graph is just that, a graph that is continuous throughout its shape. So you can see that those are the main differences between a discrete and continuous graph. Now, whether a graph is continuous, or if a discrete or continuous graph is a function or not, we're going to use a basic tool to help us out. And let me show you what that is while I write these down. So here are two examples of discrete graphs. One is a function, one is not. Notice I have two continuous graphs there. One is a function, one is not. But remember your definition of a function. It is a specific relation in which every x value has exactly one. So how in the heck are we going to figure out which one's true if I have these x values? Well, vertical line test makes it easy, because whenever you draw a vertical line, if you draw a vertical line and it only crosses your graph once, it is a function. Now, if you're able to draw a vertical line and it crosses the graph more than once, then it is not a function. Now, why is that true? Because notice when you draw a vertical line, you're really testing to see that if there's multiple values for that x value. This x value here is a 2. It is going to have two y values, and it's going to be those intersection points, which are 1, 2, 3, 4, 5, 6. And this one, let's just call it a 3. So, of course, if you can visually draw as many vertical lines and you can see that it only crosses once, it's a function. But if it's not, you need to also be able to read the graph and tell me what is that x value, what is that vertical line really telling you? Because I don't want you to say, hey, is this a function? You say no, and then I say why, and you say because of vertical line test. Vertical line test is a tool to help us figure out the definition of a function, which is having multiple y values for an x. All right, so luckily for us, this continuous graph is a function because I can draw as many vertical lines, and notice it only touches the graph in one location. Unfortunately, it cannot happen the same thing when I draw this graph. Notice when I draw that vertical line, there are two intersection points. That means that it's not a function because that vertical line represents the x value of 0. That has two y values, which in this situation, and I'm guessing by the way here, let's call that one -8, and let's call this one a +7. It has two y values. So go ahead and make sure that you got that down, and that's it. All right, so functions, telling whether graphs are a function or not, are kind of straightforward as long as you remember your vertical line test. Now, describing a graph by its domain and range could be a little challenging depending on what kind of graph you have. Now, if we have a discrete graph, like we do here, it is a little more straightforward. Because remember, your domain values are just the x values. So it's your job just to look at each one of these coordinate points and figure out what the x value is. Well, look at that x value there. I'm just estimating. I'm going to call it a -6. I know it's a -6. Now, if I look at this corner point, that x value is a 0. This one would be a positive 3. So that is literally all you have to do for discrete graphs in terms of their domain. Now, keep in mind that I am listing, so don't forget your fancy math brackets. Now let's go ahead and find the range. Now the range are y values. So this is the y-axis. I'm going to look for those y values. That right there is a negative or positive 4. Wrong axis there. Positive 4. This guy right here is a positive 2. That guy looks to be a negative 2. I've listed every single one of them. So you can see there that if you know how to read a graph in terms of coordinate points, you're going to be just fine. Continued graphs are a little bit more tricky. Let me show you what I mean. Let's say I have a continuous graph that starts here and goes all the way here. Now, unfortunately for us, we can't go ahead and be like, okay, the x values are whatever this x is and this x, because there's an infinite amount of little dots that you could choose. There's fractions, there's negatives, there's fractions of fractions. There's no way you can list all of them. So you need to use a different way of pretty much telling the reader, hey, these are the x values, or if you're talking about range, the y values. Now, the way we do that is inequalities, because an inequality pretty much tells us, or compound inequalities to be exact, what values exist greater than or less than. So if I'm looking at this guy and I'm trying to figure out the domain values, this is a continuous graph. It's continuous from the start of somewhere to the end of something else. What is the first x value that this starts at? Well, this is 1, 2, 3, 4, 5, 6, 7, 8. This is negative 8. Notice that it's going to have every x value there until you get to this x value. And let's call that a positive 8 just for time's sake. Now you can see that this is my domain. My domain is all the x values between negative 8 and 8. So how are we going to do that using interval notation? Well, my least value is a negative 8. My greatest value is a positive 8. Now, is it including those values? Yes, because there's clearly a closed dot. So that means that my domain values exist from negative 8 to 8. Now let's talk about range. Now range is y values going up and down. So what's the farthest down? I like to think of this as a map. What's the farthest south that I could go? Well, let's go ahead and call that negative 6. So we'll go for negative 6. It's going to be continuous, all these y values, till you get to this last point up here, which is represented by whatever that y value is. Let's call it a 7. Now they're closed dots, so let's make sure we put brackets to tell the reader, hey, we're including those values there. Now, of course, continuous graphs are a little bit tricky. There's a lot of different things that could go on. So let's go over a couple examples to make sure that you got it down. Now I'm going to skip over discrete graphs for continuous because they're pretty straightforward. Find your x values, your y values, and you're good to go and list them. Now, this is where things get tricky. Let's make sure we got these down. Now, looking at this first one here, I can see automatically that's a continuous graph, so I'm going to have to use interval notation. Now, is this a function? And the answer would be no. Draw any vertical line that you want. I can see here that it crosses my graph twice. So, when you say no, it's a function, you got to tell me what the x value is. This x value here is 0. It has two y values, one at 5 and one at negative 3. So automatically, I know that it's not a function because that x has multiple y's. Now let's go ahead and find the domain. Now, when I think of finding domain, I treat it differently than finding the range. Domains are x values, left to right. So if this was a map, what's the farthest west? What's the farthest left that I could go? What's the least value? And no matter what, if this was a map, this is the least I could go. This is the farthest, which in this x value is a negative 4. Now this is continuous, so this is going to continue throughout until you get to the very end here, which is in this situation a positive 4. Now keep in mind that we are including it. Those are solid lines. You could travel to 4 and it'd be okay. So that means I would have brackets on both of these guys. Now let's go ahead and find our range, and our range are y values. So think up and down. Now what's the farthest down? If this was a map, what's the farthest south you could go, which is all down here? That y value is a negative 3, and it can go all the way to a positive 5. Now we're including those values, so they're brackets, and that's all you got to go. Let's do. All right, so is this one a function? The answer is yes. No matter what, I can draw as many vertical lines that I want, and you'll notice that it does not cross that graph more than once. Now, this is where things get tricky, because although I know the basis of domain, This graph looks to stop at -6. That's the farthest left I could go, because remember, x is left and right. This looks like the farthest I can visually, but what is this arrow really telling you? That it's going forever and ever. So it goes all the way to -infinity. Now, if I look at the farthest right, it looked like 3 is, but I know that this arrow goes forever and ever, so it also goes to positive infinity. Now, keep in mind you have a very special situation. Whenever you have an interval that goes from -infinity to positive infinity, that's all the numbers you can think of. This is the same thing as all real numbers. You can either spell out all real numbers or draw 2 sticks like I did there with an R over it. That lets the reader know, hey, it's all the real numbers. Every x value is touched by that graph. Of course, you could always write out real numbers, all real numbers, but of course, writing that fancy R is a little bit cooler and it's a little, save you a little bit of time. Or let's do range. Range or y values, so north and south. What is the farthest south? Well, it looks like I could go there, but am I really given that arrow? No, so it's going to go all the way to -infinity. What's the farthest north? If this was a map. Well, it'd be right here in this location. Notice that x is a +1. It's including 1 because it's a closed dot there, so I'm going to make sure to have my bracket. Remember, parentheses are always there. Now, this is pretty much telling me that this graph exists from all the way to -infinity. It's going to go down as much as it wants, all the way to 1, which makes sense because your graph only exists below that line. All right, one more example just to make sure that we hopefully have some understanding of this guy. All right, is this a function? The answer would be yes. There is no vertical line that you could draw it across more than once. Let's look at domain values. Now, if I'm looking at the least x value, I like to go to the left. What's the farthest left there? Well, it's at 2, -2 to be exact. Now, notice that you have an open circle. Open circle means not to include that value. So I'm going to make sure to put a parenthesis because, again, that open circle is telling me to not include that value of -2. Now, if I'm going to the right, notice it's going to go forever and ever and ever. So here is the right with my little infinity. It's going to keep going forever and ever, and that's all I got there. Let's go ahead and jump to the range. Let's change colors just to have that visual of we're changing our mindset. We're doing y values, north and south. What's the farthest south? Well, the farthest south right there is a -2. It's not including it because, again, it's an open circle. It's going to go all the way to infinity. So there is that. That's really bad infinity. There it is. After that, you're pretty much good to go. Don't forget your parenthesis because technically it's interval notation. And that's it. So keep in mind that there is no homework today. We will continue with some additional practice on this on Monday. And that's it.